So for our next topic, we're going to continue with truss analysis, but introduce a different technique. In our project, we used the method of joints, and we drew a force diagram, and we looked at where the truss members were connected and wrote down equilibrium conditions. And that works great, but it means that you have to solve the entire truss to find all of them. If you only wanted, say, one particular member, then you could use the second technique known as the method of sections. So if, for instance, we were just interested, say, in the tensile or compressive force in this FC member, we could use the method of sections. Now, our starting point is still the same, meaning that we first perform external force analysis. So we see that this is pointed at A and E, so we're expecting reaction forces at A and E, which we'll just add to the diagram here now. So this will be the reaction A, and this will be reaction E. So let's write out, well, first of all, our coordinate system. We'll use the standard one with y up, x to the right, and then z coming out at us. And then we'll sum y forces, and this is going to sum to 0 because it's in equilibrium. So we've got reaction A upwards, reaction E upwards, then we've got 5 kilopounds down and 3 kilopounds down, summing to 0. Now you can't solve that equation directly, you need to use another equation. Let's sum moments about the point A, and again that's 0 because we are in equilibrium. So we have 5,000, and that's clockwise into the page negative z moment. So 5,000 pounds, and each of these segments is 4 feet long, so that's acting 8 feet from the point A. And then we have the 3,000 pound force. That's 3 segments, that's 12 feet from the point A. And then in the positive direction, we have our E reaction moment. That's 4 segments, or 16 feet away. And now we can solve these equations and find those two external reaction forces at the supports. So we find the A reaction force is 4750 pounds, or sorry, 3250. That was the E reaction. Of course, the E reaction is going to be a little bit more because there's more force applied on that side of the structure. So the A reaction is 3250 pounds. We actually have to solve first for the E reaction, and that's 4750 pounds. Okay, now that we have those reactions, we'll be in a position to find the force in this CF member that we're interested in. So here then is really the example. In order to find that CF internal force, we're going to have to make a section, a cut through the structure that includes cutting through the CF member. So one that would work, you got to cut all the way through, would be this one. Now when we do that, we're going to imagine the internal force at this point where we've cut it on this side of the structure and on this side of the structure. So we're drawing here internal forces. So there's the structure. We sort of, in our minds, mentally cut it apart. And we'll need to do a little bit of trig here. Well, let me draw a better line than that. Because, of course, we're going to, in this, to apply the conditions for equilibrium, we're going to need to know what these angles are. Turns out, because this is 4 and 4, this is 45, so this will be 45 degrees. And then we'll call this one alpha. This is 4 feet over, and this is only 2 feet up, because it's 6 feet. For GC is 6 feet, and FD is 4 feet. So that means G to this point is only 2 feet. And this is 4 feet, because CD is 4 feet. So we can easily enough find that angle alpha. Now, again down here, let's draw that line again. So this is the right half of the structure, and what we've just said is, okay, we need the angle alpha, and we have a 45 degree angle here. Alpha is clearly just the arctan of 2 over 4. And calculating that, we get 26.56 degrees. And now, thinking about the forces, we will assume that they are in tension. Okay? And so that means that the other half of the structure is going to be pulling this way on the right half. So that'll be the amount of tensile force in the CD member. We'll be pulling on the right part of the structure along the CF member and also along the FG member. Now, these are two force members, so these forces are parallel to those structural elements. And what are we going to call these? Well, we'll be really imaginative. Okay, this will be the force in the GF member. This is the force in the CF member. And this is the force in the CD member. Okay. Now, not drawn on there are the forces in the corresponding left half of the structure. There'll be a CD tensile force, a CF tensile force, and a GF tensile force. You could analyze either the equilibrium of the left half or the equilibrium of the right half, and both will give you the same solution. So let's just put here. All are assumed to be in tension. If we get a negative answer, that means the force is opposite and it's actually in compression. We should also draw on this diagram our previously calculated E reaction force right here. And that we worked out, reaction E. We know that was 4750 pounds. Okay, so now we're going to apply the conditions for equilibrium. So forces are going to sum to 0 on this half of the structure, and moments are going to sum to 0 on this half of the structure. So let us start with moments. Now, a good place to take our moments is going to end up being, well, you could choose any point, but point D is good because it eliminates the FCD unknown and also this 3,000 pound weight. So about the point D, we're going to have 3 moments. There'll be the moment of this E reaction force acting 4 feet away, and then the 2 horizontal components up here acting also 4 feet away. The vertical components of these forces act along the FD line and therefore have no moment arm about the point D. So for our moment equation, taking moments not about C but about D actually, summing moments about D. So as we said, we had reaction E, and that's acting 4 feet from the point D, and that gives us a anticlockwise or positive Z moment. Then we've got the 2 horizontal components. So cos 45, because the horizontal component of CF will be a cos 45. The horizontal component of GF will be a cos alpha, and we know what alpha is. Both of these act 4 feet. So the cos alpha component acting 4 feet away, and all of that sums to 0. Just trying to give myself a tiny bit more room there. There we are, equals 0. Okay, now we know what reaction E is, but there's 2 unknowns in that equation, so we can't solve directly. So then we use force equilibrium as well. So summing forces in the x direction, well, they're all pointed to the left, so clearly one of them is going to end up being in compression. So we've got the FCD force, which lies along our x-axis. Then we've got the 2 x components, the cos, and then we have the FC cosine 45, and so those x components sum to 0. In the y direction, we have reaction E, we have the downwards 3,000 pound weight, we have a downwards FC sine 45, well, sorry, an upwards GF sine alpha, I'll just do it so it corresponds with this. And then a downwards FC sine 45 component. So you see the GFY component is up and the CFY component is down. That's the reason for that change there. Okay, so now we have three equations and three unknowns, and this could be solved in a variety of ways. Using, say, Wolfram alpha or using matrix algebra. Then what you find is the CD force is 4750, GF, these weren't what we were asked for, but they're part of the solution, sort of come out in the wash. And the FC, the one we're actually looking for, we find that it's not in tension, it's actually in compression. Both of these are actually in compression. And the one we were looking for is 589 pounds. Okay, so that's how the method of sections works. Cut the member that you're looking for as part of a complete cut through the structure. Well, sorry, first do external force analysis, then cut through the structure to find the internal force for the member you're looking for, and solve, apply the conditions of equilibrium and solve. So having done one, it's now time for you to try one. So here's a truss. It's connected to a wall at the points A and G. And we're looking eventually to find the tensile or compressive force in the FC member. So we first start with external force analysis. So we draw the forces at the G and at the A support. We use a standard coordinate system. And then we're going to apply equilibrium conditions to try and solve for these external reactions. So let's agree to take moments about A and write X and Y force equations. Please pause the video, write out these equations, and solve them. Then play the video to see how you did. All right, so check your moment equation. So you have a negative Z moment from GX, and then also negative Z moments from these three weights. So clearly the GX force is going to end up in the opposite direction. It ends up as a negative number. So it was to the left, right? It's got to give us a positive Z moment to balance these three negative Z moments. In the X direction, so having found that, you can then solve for AX. In the Y direction, though, there is degeneracy here, and we can't actually, all we could say is that the two verticals balance those three applied forces. We don't know how much one is or the other. So having completed the external force analysis, the next thing to do then is to make a section that will enable us to find the FC force. So a good section would be straight down through. And then having done that section, here it is here, your next task, let's agree to analyze the forces on the right. We can analyze the forces on the left and it gives us the same answer. But let's agree to analyze this part here. So draw the force diagram for this, and then write out the equilibrium conditions. Pause the video, try that now. Notice that this angle, because it's 4 over and 4 up, this angle is 45 degrees. So it's quite straightforward. So pause the video, then do your work, and then compare. Turn the video back on and compare with my answers. Okay, so 4 feet, 4 feet. Hopefully you realize that point C was the best place to take moments, because then there's 1, 2, 3 forces passing through C, whose line of action passes through C, and there's no moment. So then you just have the weight at D, and then the EF internal tensile force giving you a moment. So there's your moment equation, and then X and Y forces sum to 0. So if you got those, that's great. Then just take a minute and solve those equations. Pause the video, get your answers, and see ultimately what the FC force is. FCF force, this tensile force right here that we're looking for. Okay, so these equations solve pretty easy because you can get the CF just from this equation. You can get the EF from this, plug it back in and solve. You should find the CF force that we're looking for is 1980 newtons, so it is really in tension. Then the EF force works out to 800 newtons. And then the BC force is actually in compression. It's minus 2200 newtons. And it's not really surprising that that ends up in compression, because if you look, you could see due to these weights, the structure is going to have a tendency to sort of sag downwards. And that's going to stretch out the EF member, but it's going to compress or squeeze together the BC member. So it's not surprising that the BC member is actually pushing to the right. It's actually in compression. And that's what our answer has shown us. So these two simple problems give you some insight into the method of sections. It's another method of truss analysis that can be used when you're only looking for one or a small number of internal forces, as opposed to solving the entire truss. It's just a little faster and a more direct way of solving. So in class, I'll do a problem for you, and then you'll work in groups on a bunch of problems using this method.